For centuries, we have gazed into the night sky, listening to the stories told by the light of distant stars. We've built telescopes to see deeper, farther, to uncover the secrets hidden within the cosmos. But light is only part of the story. There's another, more subtle language that the universe speaks, a language of ripples and echoes written into the very fabric of space and time. Welcome to the era of gravitational wave astronomy. Gravitational waves are ripples in the fabric of spacetime, predicted over a century ago by Albert Einstein. Unlike electromagnetic waves, such as light, radio, or X-rays, which are vibrations of electric and magnetic fields, gravitational waves are distortions in the very structure of space and time itself. They're created by some of the most violent and energetic events in the universe. Einstein's general theory of relativity, published in 1915, proposed that massive objects like stars and planets do not simply exist in space, they warp and curve it. This distortion is what we perceive as gravity, but Einstein went further. He suggested that when these massive objects accelerate, when they move, collide, or explode, they create ripples in spacetime. Much like a stone thrown into a pond creates ripples on the water's surface. Gravitational waves are produced by cataclysmic events, collisions of black holes, explosions of supernova, merging of neutron stars. These waves travel across the universe at the speed of light, carrying with them information about the events that created them. They tell us about the nature of gravity, the properties of black holes, and the birth of stars. But gravitational waves are incredibly weak by the time they reach us, having traveled billions of light years across space. Detecting them requires instruments of unprecedented sensitivity, machines capable of measuring changes in distance smaller than a fraction of a proton's width. An instrument, the result was LIGO, the Laser Interferometer Gravitational Wave Observatory. It consists of two massive detectors, one in Washington and the other in Louisiana, designed to detect these faint ripples in spacetime. Their construction marked the beginning of a new era in the search for gravitational waves. Gravitational waves do not just pass through the vast reaches of space, they also pass through us. As these waves travel across the universe, they stretch and squeeze the space they move through, causing distances between objects to change. But the question arises, do gravitational waves stretch us too? Theory, yes. Gravitational waves do stretch and compress everything in their path, including us. However, the effect is incredibly tiny. A passing gravitational wave would stretch you by less than the width of an atomic nucleus. It's so small that it cannot be felt or noticed in any way. At LIGO, the world's most precise measuring device, a laser interferometer, is used to detect these minuscule changes. The device splits a laser beam and sends the two halves down perpendicular arms, each several kilometers long. When a gravitational wave passes by, it changes the length of these arms by a tiny amount, altering the interference pattern of the light. This change indicates that a gravitational wave has passed. Thus, while gravitational waves do indeed stretch us, their effects are so minute that they can only be detected by this most advanced technology, like the instruments at LIGO. Through these ultra-precise measurements, we are able to hear the faint whispers of the universe. Gravitational waves are not just distortions in spacetime, they also carry energy. When massive objects like black holes merge, they release an enormous amount of energy in the form of gravitational waves. This energy travels across the cosmos, rippling through spacetime and revealing the most powerful events in the universe. The first detection by LIGO in 2015 confirmed that these waves carry energy away from their source, causing the black holes to spiral towards each other and eventually merge. The amount of energy carried by these waves is staggering. In just a fraction of a second, the merging black holes emitted more energy than all the stars in the observable universe combined. This discovery not only confirmed Einstein's theory, but also opened a new way to understand the most energetic processes in the universe, revealing information about the objects and events that created these waves. Each detection tells a story of the formation and evolution of black holes, neutrons, stars, and even entire galaxies. The energy carried by gravitational waves does more than just stretch space. It allows us to map the universe's most extreme environments, to understand how black holes and neutron stars form, and to explore the very nature of space and time. Gravitational waves not only affect the space they move through, they also have profound effects on the very objects that create them. When two massive objects, like black holes, merge, the gravitational waves they emit carry away significant amounts of energy. This loss of energy directly impacts the motion and structure of the black holes themselves. When neutron stars collide, the effects are even more dramatic. Gravitational waves not only strip away energy, but also determine the final outcome of the collision, whether a new, more massive neutron star is formed or whether the stars collapse into a black hole. These waves provide clues about the internal structure and composition of these dense, enigmatic objects. The gravitational waves we detect are signals from the heart of cosmic violence, revealing the forces at play, the incredible energies involved, and the final fate of these cosmic giants. They help us understand how stars live and die, how black holes are born, and how matter behaves in the most extreme environments imaginable. To detect gravitational waves, scientists needed to build an instrument unlike any other, the Laser Interferometer Gravitational Wave Observatory, or LIGO. Its design is based on a simple but powerful idea, using light to measure the tiniest distortions in space. The principle behind LIGO is simple in concept, but complex in execution. A powerful laser beam is split in two, sending the light down two long arms, each 4 kilometers in length. At the end of each arm, mirrors reflect the light back to the central beam splitter, where the two beams are recombined. In the absence of gravitational waves, the beams cancel each other out perfectly due to their carefully calibrated paths. However, when a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction. This changes the length of the arms, altering the time it takes for the laser beams to return and creating a distinctive interference pattern that LIGO's detectors can measure. To detect these incredibly small changes, LIGO must operate under extreme conditions. The entire interferometer is housed in an ultra-high vacuum tube to eliminate air molecules that could scatter the laser light. The mirrors are suspended by finely tuned systems that isolate them from ground vibrations caused by traffic, wind, or even distant earthquakes. LIGO is not alone in its quest to detect gravitational waves. Across the globe, a network of observatories works together to listen to the universe, combining their data to improve the precision and reliability of detections. Virgo, located near Pisa, Italy, is LIGO's European counterpart. With its 3-kilometer-long arms, Virgo uses the same principles of laser interferometry to detect gravitational waves. By collaborating with LIGO, Virgo helps pinpoint the location of cosmic events, allowing astronomers to direct their telescopes to the right part of the sky at the right time. In Japan, the Kagra Observatory brings new innovations to the field. Located deep underground to shield it from surface noise, Kagra also uses cryogenically cooled mirrors to reduce thermal vibrations, making it even more sensitive to gravitational waves. By combining data from detectors on different continents, we can determine the location of gravitational wave sources with much greater accuracy. When a gravitational wave passes through Earth, it arrives at each observatory at slightly different times. By measuring these time differences, we can pinpoint the source of the waves in the sky. The global network has enabled us to conduct multi-messenger astronomy, where gravitational waves are observed alongside light, radio waves, and gamma rays. Together, they paint a fuller picture of the most extreme cosmic events. Gravitational wave astronomy is truly a global effort. Scientists from every corner of the world are working together to unlock the universe's secrets, proving that in science, collaboration knows no borders. Gravitational waves come in a wide range of frequencies, each frequency revealing different stories about the universe. LIGO and its partner observatories are tuned to capture specific frequencies that align with some of the most energetic events in the The Cosmos LIGO is designed to detect gravitational waves in the frequency range of approximately 10 Hz to 10,000 Hz. This range is well suited for capturing waves produced by events like the merging of stellar mass black holes or the collision of neutron stars. These frequencies fall within a range similar to that of human hearing, but instead of sound waves traveling through air, they are ripples traveling through spacetime. Each gravitational wave signal can tell us about the objects that created it. For example, a merger of two black holes produces a chirp, a wave pattern that increases in frequency and amplitude as the black holes spiral closer together, culminating in a sudden peak as they merge. The unique signature of each chirp allows scientists to determine the masses, spins, and distances of the merging objects. However, not all gravitational waves fall within LIGO's detection range. Lower frequency waves, such as those produced by the mergers of supermassive black holes found in the centers of galaxies, lie outside LIGO's current capabilities. Detecting these lower frequency waves requires different types of instruments. This is where the future of gravitational wave astronomy comes into play. The planned Laser Interferometer Space Antenna, or LISA, will be positioned in space to detect these lower-frequency gravitational waves. By expanding our observational range, LISA will allow us to hear the deep, slow rumblings of supermassive black hole mergers and other cosmic phenomena, further extending our understanding of the universe. By broadening the range of detectable frequencies, we will open up new windows into the universe, enabling discoveries from the high-pitched chirps of merging neutron stars to the low-frequency growls of supermassive black holes colliding. Each new frequency band brings with it new opportunities for understanding the cosmos. In August 2017, a groundbreaking moment in astronomy took place. For the first time in history, an astronomical event was observed in both gravitational waves and electromagnetic radiation. This event, known as GW170817, marked the dawn of multi-messenger astronomy. GW170817 was the merger of two neutron stars, the remnants of massive stars that had previously exploded as supernova. As these neutron stars spiraled together, they emitted gravitational waves, which were detected by LIGO and Virgo. Just 1.7 seconds later, NASA's Fermi Gamma Ray Space Telescope observed a burst of gamma rays, pinpointing the event's location in the sky. This unique observation triggered an unprecedented global effort. Within hours, dozens of telescopes across the planet began observing the region in different wavelengths, from radio to X-rays, allowing scientists to study the event in detail like never before. The first ever joint observation provided critical insights into the universe's workings. It confirmed that neutron star mergers are key sites for producing heavy elements, such as gold and platinum, and scattering them throughout the cosmos. This was a long-suspected theory, but proven with direct evidence from gravitational waves. The discovery of GW170817 demonstrated the immense power of combining gravitational wave and electromagnetic observations, allowing us to witness cosmic events with greater